introduction to high performance computing, including an overview of system architectures and some hands-on exercises where we'll submit some jobs to the ARCHER2 cluster here at the University of Edinburgh. My name is Tony Hallam, and I'm going to be your instructor for the entirety of today. There'll be a couple of offsiders who'll be helping me through the chat and breakout rooms. This morning it's Juan again, so if you have any technical questions or issues, talk to him. If there is anyone new joining us today and you haven't been able to log on to the ARCHER2 computer via SSH, please drop Juan a line because we'll be doing that a little bit later. For those of you who were with us yesterday, the issues with logging into ARCHER2 seem to be resolved. I was able to log in this morning, so hopefully we won't have the same disruptions that we had yesterday during today's lesson when we really need access to the cluster. Just like yesterday, these sessions are much better for everyone. I know they're virtual. If people are prepared to ask questions, drop them into the chat anytime. I've got it open so I can keep a tab on what everyone is saying, and any comments or queries you have. It's always easier to answer these things during the time than to revisit them at the end of the day. All right, if there are not any issues, we might crack on. Today's lesson, I'll just share this website here, is available from this URL, which I'm just pasting here in the chat. We're basically going to be covering the content of this website. The material was not written by me, but I'll do my best to help you guys work through it. We'll have a number of what they call episodes, but kind of chapters that we're going to cover two this morning, where there'll be quite a little bit of talking as we discuss some concepts related to HPC and some small exercises just before the break. After that, we're going to start to use the scheduler on ARCHER2, and we'll discuss a little bit of what that is and how it works and why it's necessary in a HPC environment. And then we'll have a lunch break, just an hour and a half today, because we've got quite a bit of material to cover this afternoon. And then we'll talk about a few more advanced HPC concepts that you need to know to be able to use and make the most of HPC systems. Right. If you have not, or if you weren't part of the session yesterday, you do need to follow the setup step. Please do that now if you can. Juan is available to answer any questions that you might have. All right, so let's crack on and ask the question, why use a HPC system? So we kind of touched on this yesterday, and you know, you're all here, so I suspect you have a problem or a program in mind that you want to run for your own research or your own tasks. But generally, we can break HPC, or the reason to use HPC, down into a few different types of problems. The first problem is relatively simple to understand. Essentially, you might have a very small model or a very small data processing task, or even a slightly large one, and it's very runnable on your local desktop or your laptop. But the problem is you might want to run that task thousands or hundreds of thousands or even millions of times. And if each task takes a minute or even 10 minutes to run, you're looking at, potentially 1 million minutes to complete the whole process. So running each task sequentially is what we call a serial process. And nowadays, we often talk about this idea of running things in parallel. So we want to run more than one task at once. You can do that on your laptop as well, but your laptop has a limited number of processing units or cores that it can run that task on. So what HPC does is it allows you to get access to a large number of cores so that you can significantly reduce the amount of time that it takes to run many versions of your task. Another situation that's quite common is we generate an enormous amount of data these days. There are some data acquisition processes or image scanning technologies that can generate beyond gigabytes, terabytes, or even petabytes worth of data. I think for the National Aerial Photography database here in the UK, we were looking at something like 5 petabytes of data, which is, far beyond anything that's possible to contain within a single computer. And in those instances, if you want to have access to all of that data and you want to be able to run computations on it, you need more storage, you need more memory. And a lot of those resources just aren't available at the user level. So user level being your laptop or desktop. You can't build a computer big enough to essentially handle what you need. So you need to go to essentially much larger composite systems like we have in HPC, or even distributed memory systems, which we'll sort of talk about. So HPC makes those really large data problems feasible in the sense that you can do the task efficiently and even at all, something that might not be possible on your user system. And then the last type of task that's also reasonably common is we try to do modeling, maybe like in this instance, they use the idea of fluid dynamics modeling, but meteorological modeling, like weather modeling, is also quite a common task. And these models require a huge amount of compute power because they have quite complex algorithms and a large number of, essentially, the model needs to be discretized, so it's broken down into a large number of cells that then need to be computed over, and that is an iterative process. So you're doing it many times, essentially, doing a time type simulation. And those types of jobs require a huge amount of compute. And you could run them potentially on your laptop, but they would take an enormous amount of time. And so people have developed ways to kind of break these large problems down into littler tasks that can be distributed across a distributed memory system. And that's one of the perfect applications for HPC. So it might be interesting at this point just to think about maybe some research or some data analysis that you want to do. I'd be interested if you want to drop into the chat which box you think your work's going to fit into. Of course, during this course, we can't kind of cover how to solve all of these problems, but just for the interest of seeing where you're all coming from, it might be nice to see what you're doing. Thanks, Johnny. Yeah, parallelizing multiple runs. So that's what we call like an embarrassingly parallel task, because you're just taking a single serial task and running it multiple times. Yeah, very good. That's the top one. Cool. Lots of data. Yeah, nice. All right. Cool. All right. Okay, so I'm guessing that one is the top one, running lots of statistical simulations. Yeah. Yeah, these are all pretty common tasks. I mean, as part of my PhD, I was running lots of porous media modeling simulations which sit in the bottom problem. So that's a costly process to do. And I was running genetic algorithm optimizations. So I was running those models lots and lots of times. So it was kind of like a hybrid of lots of embarrassingly parallel model runs with an overarching desire to tune this model. So yeah, there's lots of different applications, but you can kind of see how you need bigger computers basically to solve the types of problems that we're running into these days. We have so much data, we have algorithms that are so complex, and we have time constraints, which mean they're not possible to run locally. Cool. So let's talk a little bit about the anatomy of a standard laptop, because this will help us understand how HPC processes and how HPC and what will actually be feasible when you go to HPC. So we have most people working on either a laptop or a moderately sized desktop computer these days. That laptop has some input that the user can do. So usually this is a keyboard or touchpad and mouse. This is how you interact with your computer. Internally, the computer has what we call a central processing unit or a CPU. Usually it's just one. And in the old days, each CPU used to have just one core. So that's one core that was able to process instructions that you sent it. But these days, as you know, a lot of CPUs actually have 2 or more cores. So often you can just open up your task manager and see how many cores you have on Windows, for example. You also have a bank of memory. So memory is basically volatile storage. That means that it is storage that basically is wiped whenever the power is cut to it. But memory itself, also known as RAM, is very fast. And it acts as an intermediary storage position between your hard drive and your CPU. So if you were to do everything from your hard drive, the bottleneck would be your ability to get data from the hard drive into the CPU. So the memory acts as a little bit of a buffer there. You can preload large amounts of information into memory and then push it to your CPU very quickly so that the CPU isn't bottlenecked by its access to data. You then also have some output that you can use. So that sort of includes the display, maybe some audio, your disk, and your network connections. So maybe you're sending, network would also act as an input, say. So this is where you're sending and receiving information from. Sometimes, though, this isn't enough, and I'm guessing that most of you have run into this problem. That's why you're here for this course. You either don't have enough memory or you don't have enough compute. And so you need to scale this up. And one way you can do that is you can just have bigger computers, computers that don't feasibly fit into a laptop or into a moderately sized or reasonable desktop computer. And so these are often called, just basically servers. Servers are essentially computers that don't have direct input from users. So they don't usually have a keyboard or mouse. They do have disk and network access, and they don't usually have a display. And they may have multiple central processing units and a single bank of memory. So sometimes you can get servers that have multiple physical CPUs, and then each multiple physical CPU will have multiple cores within them. Servers are generally designed to do very specific tasks. So in this instance, they talk about servers which are used for routing information between different systems. So you might not realize this, but there are many servers that sit between you and other computers or websites on the internet. And those servers, the only job they have to do is to work out how to most efficiently move information from Google or the BBC News or whatever else it was that you were looking at this morning to your phone, so that you get that information in a reasonable amount of time. There are also servers that just run websites. There are servers that offer your cloud storage, like OneDrive or Dropbox, if you use them. There are servers that run the applications that you access through the web, like Microsoft's O365 products. So these servers exist everywhere, and they're usually administered and commissioned to do specific tasks. But that's not particularly useful when it comes to the types of problems that we're trying to solve in HPC. And that's where we start to basically build what we call clusters. And clusters essentially are basically generic servers that we pool together to build supercomputers. And these pooled resources essentially allow us to submit jobs that are then distributed across those shared resources in a fair and equitable way based on maybe a charging model or some other kind of sharing model that the cluster you're using has. But because they're headless being they don't have a display, they don't have a keyboard and mouse, they just essentially sit in a server rack in a data warehouse somewhere, or maybe in a back refrigerated room in your university or research building. They have to be accessed over the network. So this is the SSH that we were doing yesterday, and using a shell. So that is using a command line interface. And that's the only way to get access to them. And because of that, they don't usually offer a graphical user interface. That's very rare for graphical apps to be used from a cluster. And you submit jobs that essentially are fixed pieces of work to be run. So you don't often have something running on them constantly. You just give it a small piece of work, get some results back, do some analysis, decide whether you need to change things or run something else or a new job, and submit that. When you have a large number of computers joined together like this, the individual computers, so the individual servers that have shared memory and have the compute cores, are what we call nodes. So you can think of a node as being like a self-contained machine that often has some shared memory. So the memory or the RAM can be accessed by all the cores on that machine. It may have one or more CPUs, and it will have the number of CPUs plus multiplied by the size of the cores. So what do I mean by that? I mean, so if you have 2 CPUs and each CPU has 4 cores, then the total number of cores on the machine will be 2 times 4, 8 cores. And all those cores will be able to access the memory on that particular node. If you were to go to another node, it would not have access to the memory in that node. So these nodes that you have in a cluster, they often define like the maximum size of a problem that you can solve on a single node. And if your problem can't be solved on a single node in a single bank of memory, and you have to use more than the memory available in a single node, then you have to go to what's called a distributed memory problem. And that's a little bit beyond what we're going to talk about today, but essentially there are lots of protocols and software available that will help you distribute your large memory problems across. Yeah, thanks, Swan. Yeah, the GUI also consumes lots of resources, so having GUI definitely can detract from the overall experience for multiple users. You've got to remember that clusters are shared resources in the sense that there may be tens to hundreds or even thousands of users on them at any given time, and it needs to be able to handle the requests that users are passing to it. We're going to talk a little bit about that later this afternoon when we talk about equitably using clusters. There's some other things I'd point out at this time. Sometimes a cluster will be homogeneous in the sense that every node will be the same. So when that happens, you could say, okay, well, node 1 through 10 will, which are the nodes in my machine, they all have 256 gigabytes of RAM, and they all have 4 CPUs with 4 cores each. So we have 16 cores per machine, and they all have access to a given network storage. But that's not always the case, and ARCHER2 is a good example of this, where often large computers will have different types of nodes designed to do very different types of jobs. Some nodes might be super large memories, so they might have 2 or 4 times as much memory as the standard node. Some nodes might have more CPUs and cores than others, if possible. And what's becoming more prevalent now is that we're seeing a lot of nodes that are often given what are called GPUs, or graphics processing units. And graphics processing units are very specialized CPU cores that are good at doing what are called floating point operations. And some software can take advantage of that, and it will accelerate your ability to compute problems significantly. Machine learning, particularly convolutional neural networks, are a really good example of where GPUs can make a big impact on the time it takes to train your models. Just gonna skip over this one. I think we've kind of covered most of that. So the main points, the takeaways from this little session are high performance computing typically involves connecting to, like a very large computing system somewhere in the world. It could be in the office next door, it could be in the building 2 blocks over. In the case of ARCHER2, it could be, 10 miles outside of Edinburgh. Wherever your HPC system is, you will connect to it remotely usually from your local laptop or computer. They're designed and made available specifically to do work that isn't possible on your smaller systems. And the standard way of interacting with them is via the command line, which we did yesterday using the shell, or specifically bash in this case. Does anyone have any questions on why use a Hpc system? I'm guessing because you're all here, it's kind of part of the course that we want to use Hpc, but maybe there's some outstanding queries. Okay, let's kick on to, okay, got one question. All right, yeah, good question. So we'll talk a little bit about the architecture of Hpc systems, but generally nodes will have a little bit of storage locally, what they often call scratch, which is a very high performance local disk that you can use to store temporary results. And you can either work on a node using its scratch, and then your script will have to copy that work back to a shared file system. Or if you don't have too much data, you might get away with reading your data directly from a shared disk. So you can think of shared disk as being basically like network attached storage. So, like a network drive in Windows, or I'm not sure how they mount network drives in Mac OS, but think of it as being like your company or your university's shared disk, where you can access it from any computer that you log in. You probably need to talk to the for your Hpc system, it's probably best to talk to the administrator of the system or the help desk of the system, and to find out what the architecture actually is, what their preferred way of managing data input and output is, or even whether your data will fit into the scratch on the local disk. It might not, in which case you'll have to stream it from the shared storage. But yeah, good question. We can, actually, we'll kind of cover this a little bit this afternoon when we talk about the /work directory on ARCHER2, because that is essentially shared disk. The home directory is not visible on any of the nodes. So we'll kind of see how that works. Yeah, so home and work are shared on the login nodes, but I don't think home's available on the compute nodes. Yeah. All right. So I think we've kind of covered some of this, but let's just talk about some generic terms which I think sort of get thrown around a lot these days, but perhaps with not a huge amount of understanding of what they actually mean. And specifically, we're going to talk about cloud, cluster, high performance computing, which is often abbreviated to HPC. So the cloud, in the modern sense of IT, is often used to refer to essentially computing resources or applications or storage or anything that essentially is provisioned to you on a as needs basis. So, and these are resources that can be essentially virtualized from anywhere. Good examples of this are like Office 365 in your browser, Google Docs, Gmail, what's another good example? Lots of businesses will use AWS, which is Amazon Web Services, their cloud infrastructure to serve things like login servers, databases, storage. So, for example, your OneDrive and stuff is all storage in the cloud, essentially. And it's become this kind of catch-all that isn't necessarily a useful description of what something does, other than to describe the fact that the process you're running or the data you're accessing or the application you're interacting with is not being run locally on your computer. It's being run on a computer somewhere else over the network. So if you were to disconnect your computer from the network, you would not be able to access or run that application. The cloud's become basically one of the biggest growths in IT that I've seen, I think, in my career. It is pretty much everywhere now, and companies are using it for just about everything they can. And you can kind of understand why. It allows them to pool their resources in centralized and scalable locations. So instead of having 500 companies, each with their own IT administrator looking after their own hardware and their own software, you can put all of that infrastructure and reduce the number of people needed to look after it by putting that infrastructure all in one place and just serving it in a smart way over the internet. And that's kind of being facilitated by improvements to the speed of networks all over the world and our insatiable need for everything from streaming music and videos and movies over Netflix and Spotify to just wanting, like our morning news and stuff over the internet through Alexa or Google Home. On the other hand, the term Hpc system is generally used to define large compute resources or computer systems that are designed to look after and handle computationally intensive workloads. So cloud services can often be, kind of a bit stop-start in the sense that you start up your email, you tap out a few emails, and then you just stop and you leave it kind of sitting there. And although the service is still provisioned to you, it's not actually doing anything. Whereas Hpc systems are designed to be given tasks which require the system to work at peak performance for minutes to hours to even days and weeks. So you might see some tasks like the ones that I was running for fluid simulation where a single node will be running at 80, 90 or even 100% usage for 2 to 3 days. And that's the kind of thing that Hpc is designed for. They're also not usually designed for running tasks that will run indefinitely or things that we want to serve to the internet indefinitely. So they're, again, designed for tasks that have a fixed endpoint and will start and finish. They're also designed to handle large amounts of data and what we call flops or floating point operations, which essentially are what GPUs are really, really good at. If you look at the top 500 list of Hpc systems, they are usually, sorry, what are we saying? Oh, right. So essentially HPC systems, whereas cloud systems can be somewhat distributed in the sense that you might have a database in London and a login server in Frankfurt and a server in Dublin, say. You would need a HPC system. A single HPC system needs to be more or less entirely located in the same location, because there are limits to how fast you can send information across a HPC network based on your networking infrastructure. So ARCHER2, for example, is essentially entirely within a single compound, and that is where it is. That's where it is kept. Whereas cloud systems like your Gmail or your Office 365 web login might be served from different locations at different times, depending on load and where you log in and where the data is kept and so forth, because the requirement for performance is not the same as it is in a HPC system. Finally, the word cluster is often used to talk about smaller or moderate scale HPC resources. So we wouldn't usually refer to something like ARCHER2 as a cluster. But a lot of universities and even small research groups might have a single computer or a couple of computers that are kind of tied together in tandem, and this is a small compute cluster that would then be shared within that group. That's pretty common. All right, I'm going to skip through logging in because we've kind of done this before, but let's switch to the shell and just make sure everyone can get back onto ARCHER2 today. Okay, this is coming up. Cool. Make that a little bit bigger so everyone can see. All right, so although in the documents it just has SSH user ID, remember we need to give SSH the correct RSA, the correct SSH key so that it can authenticate us when we log into ARCHER2, and we do that using the -i flag on the command line. And we're going to give it our username and the login address, and I hope everything goes here. You need to put in your passphrase for the key. So you had one passphrase for the SSH key, and then the password was your ARCHER2 login password. And hopefully you've all just seen the ARCHER2 login print-off turn up. ARCHER2 gives you some information here when you log in. For instance, you can see that I am on LN04, so this is login node 04. Remember, there are 4 different login nodes to manage the number of users that log into ARCHER2, so you might have ended up on a different login node. You can also see which login node you're on at any time. It'll tell you in the prompt, I believe. Or you can type in the command host name, and this will tell you which login node you're on. I'm going to skip the section in what's in your home directory, but quick reminder from yesterday, if you want to see where you are, you can print the working directory, pwd. It'll tell you where you currently are in the command line. And you can see what's in the current location by using the list command ls. So this tells us that I have a number of files and folders here. All right, let's go back. If anyone had trouble logging on to ARCHER2, please let Juan know. Otherwise, I'm going to jump back to the documents. Apologies, it's quite a large amount of talking this morning, but there's not really any other way to cover a lot of these topics. So we're now going to talk a little bit about the types of nodes that compose a cluster or a HPC system. I sort of mentioned that there's a number of different compute nodes, and tangentially I've mentioned login nodes, but there's actually a few different types of nodes within a HPC system, particularly as they get larger. You need more computers essentially to manage the tasks that are going on within the cluster itself or within the HPC system itself, the supercomputer. There's usually a node called the head node. You can think of this as being like the master node that controls the whole system. This is sort of like the one computer to rule them all. In ARCHER2, you wouldn't normally log into this, but sometimes the head node might be conflated with a login node on smaller systems. We've got some login nodes, so this is where you basically end up when you're trying to get your data across to the system and you're trying to set up your jobs to run. There might also be a landing pad. I'm not really sure what that's referring to, but maybe you have some more information there. And there could also be a submit node. So this might be a node that runs the scheduler and manages the jobs that people are giving to the system. And the tasks are generally split across a large number of nodes in a big supercomputer like this, because if one node goes down, like yesterday, if the head node goes down and we can't log into the system, then jobs that were running on the machine can keep running, and the system administrator just has to fix the head node. It doesn't have to worry about a lot of the compute nodes that are probably okay. Or if a single login node has problems, there might still be other login nodes that users can use. So it offers a level of redundancy and security there, so that work and services are not lost, ideally. This is a good tip. So generally speaking, the login nodes where we after logging into ARCHER2 should not be used for time-consuming or resource-intensive tasks. So it's fine to do some text editing or to use them for uploading and downloading files or setting up software and stuff, but this is not where you run your jobs. You don't log on to a login node and then start, processing, a huge amount of data using your Python or R script in this case. This is purely where you do your setup before dispatching your compute-intensive jobs to specialized compute resources. And the reason for that is because other users are also using these login nodes. So if you bung them up with compute, then other users are going to struggle to do the simple things that they need to do on the login nodes. Potentially, if you're caught running too big of tasks on the login nodes, you may get a slap on the wrist from your system admin, and it's just generally pretty poor etiquette. There may also be dedicated nodes for data transfers. Juan can probably tell you a little bit more about ARCHER2 and how data should be transferred to that system. But your system administrator will have protocols or guidelines around how to update excessively large amounts of data to a system. So we talked about them. Then we have our worker or compute nodes. So these are the nodes that actually do all of the computational work. These are essentially tasked to do work by what we call the scheduler, which is a specialized piece of software that we're going to talk about a little bit after the next break. For this lesson, we're going to use a scheduler that's called Slurm, but there are other types of scheduler out there, such as SGE, which is the Sun Grid Engine, Torque, and PBS. And your local administrator, HPC administrator, will have information about the type of scheduler that they're using and potentially some documentation about how to use it. Cool. Let's go back to the shell. So this specialized piece of software comes with a number of commands that are available through the shell. And the first one we're going to learn about is one called sinfo. If we just type that in on our login node, we get what is quite a complicated printout. I'm just going to make this a little bit wider so we can kind of see what's going on here. But this is a table with a number of columns. The first is the partition. So this is, what is the partition? It's kind of like the type of, or sort of the task type that the node belongs to. We've got an availability option. So this tells us whether this particular row is available or not. We've got a time limit. So this is how long we can run things for on this node type. We've got a number of nodes available. So this is the number of nodes that fit this type. And then we've got like a node list here. So this is the nodes that, or the names of the nodes that fit this particular type. And within here, you've got essentially a large number of nodes allocated to different types of tasks within the scheduler. So these standard nodes are all the same, and there'll be a description somewhere that tells you what a standard node is. And we can see 4 are for this drain state, 12 are in maintenance, 3 are down at the moment, 96 are reserved. So these ones are waiting for jobs, or particular jobs, I think. And then we've also got some different types of nodes here. So we've got like high memory nodes as well. So sinfo gives us a little bit of information about the types of machines that are available. And you can actually get more information, I think, by remember, you can always use the -- help on the command line to get more information about what a command does. We use the -s. Okay, so it's the 3 different types. Right. Okay, might just move on from that for a second.
Regarding the partitions, is because all the compute nodes are divided in 3 groups. We have
Yeah.
the standard one that is normally the group that you normally use, so you submit. We also have a high memory node that rather than 256 gigabytes, they have 512 gigabytes of RAM. And also there are serial nodes that normally you don't use them for parallel computation. You use them for long compilations that there are some compilations that could take let's say 8 hours or compress files, these tasks that you don't need a whole node. I think we will see that later on.
Is the time limit that was 1 hour for all node types? Is that what the
It's
time limit is?
one day is
One
the
day.
limit.
Sorry.
Yes.
Okay. Yeah, so sorry, if I bring that back up here, let me bring that back up.
We share later in the also in the ARCHER2 and the user documentation is explaining each partition what is it's
Yeah,
like
so usually,
it's
you know,
one day.
these partitions will be specific to your cluster. They might be called something else if your system's not using Slurm, but these are names given by the admin. And this time limit here describes how long you can run a job on these nodes. So, for example, this is seconds, minutes, and hours. So this is days. So the maximum job time on any of these nodes is 1 day. I assume that if you had like special circumstances, you might be able to get dispensation, or do you have to break your job down or try and improve its performance to go beyond 1 day?
Yes, the possibilities are either you can use checkpoints that after, let's say, to be safe, after 23 hours, you save the work that you have done. The next job will read that checkpoint file and continue with the process. So
Right.
in case that for some reasons you needed to run a job for 2 days, let's say, you can request a reservation. That we have seen before that some nodes have the reserve tag, means that these are in to a reservation. That means that you will only have access to these nodes for the period of time. Normally, when you request a reservation, you say, I need the nodes from Tuesday at noon until Thursday at noon. I would need the 12 nodes. You get a code and you can use that code to submit the jobs to that reservation.
Yeah. Okay. So this space it's a way of essentially managing the resource, and we'll talk a little bit about how the scheduler works after the next break. But yeah. All right. Let's quickly dash back to. Thanks for that one. All right. So I kind of already covered this idea of what is on a node, but here's a sort of diagram summing it up. In this instance, we've got a single CPU, that's this big box, that has 4 cores in it. There is what's called shared cache, which is a very small high performance storage section for storing instructions that are passed to the CPU, well, to each core actually. And then the CPU is connected to some memory or RAM, and it's also connected to some local or shared disk. And this essentially is what a node looks like. And this is pretty similar to what your laptop or your desktop computer looks like. The difference is that the nodes we're talking about often have many, many more than 4 cores. So sometimes you might have 24, 48, 64, even 128 cores on some specialized nodes, and they all have access to the same memory. Nodes aren't designed to basically store data indefinitely, so that's why we have the shared disk. Although sometimes you can get better performance or better compute performance if you copy your data to the scratch drive or some local disk attached to the node that you're doing processing on. Not necessarily, Johnny. So, I mean, it entirely depends on the hardware that the HPC cluster has, or the system has. And that might depend on its age, it might depend on the vendor that they bought their hardware from, or the type of architecture that they're running, you know. So there might be limits to, for example, to how many AMD cores can be put together with what, you know, a maximum amount of memory. If anyone's built a desktop computer, often you'll know that when you buy a motherboard and a CPU, that motherboard comes with a maximum memory limit, and the same things happen with you know, the hardware that you put into these HPC systems. So it really comes down to what was available at the time and what fit the budget or was cost effective in terms of the objectives of the system. You really just have to look at what's available and see how that fits with the problem that you're trying to solve. Okay, I'm going to quickly skip this section, although it might be interesting to look at the resources on the login node. I think everyone probably knows how to find the amount of cores and RAM on their own machine. But if you want to see, for example, the number of processors on, let me switch back here to my login node. So if we want to see the number of processors on our login node, we can type the command nproc --all, and we can see that we've got 256 cores. And we can also see the amount of memory that we have with the free-n. I wonder if I can make sure it's, there we go. This makes it a little bit usable. We can see we've got 503 gigabytes of memory, 75 gigabytes are currently used. So we can kind of see what the available resources are. Another useful command, if you're not familiar to Linux, is top, and this is like a task manager. So you can kind of see the different processes that are being run. This is similar to the task manager that you have in Windows. You can see, for example, here the number of users that are logged onto the system. You might even see your own username here. And you can see the processes that people are running and the amount of CPU that people are using. So this is you know, generally a useful command if you want to see what's happening on a system. And you can just press Q to exit out of top. You can get some slightly more detailed information if you use the less command and reference the file proc/meminfo. So this gives you a lot of information, for example, about the system. A lot of this might be a little bit complicated, but as you get into programming or trying to optimize your code, this could all be quite useful. The last thing you might want to know is how much storage is available, so that's disk space on your system. And to do that, you can use the df command. The T option here will tell us what kind of file system each resource is, and H again makes it human readable, otherwise we get everything in bytes or kilobytes. So we can see there's like quite a large number of temporary file systems in the run user _/ here. If you want to see like a specific folder, you can also pass that to df. So for example, we could see how much storage we have here in the home directory, which is dot because I'm already there, or tilde would be home directory. So we can see there's 198 terabytes of storage in this home2 directory, and only 8.9 is used. If we want to know, for example, later how much is available in the project level work directory, so remember we're going to be looking at this work directory later, because this is what will be available to all of the compute nodes. You can see that 3.3 petabytes is available and 678 terabytes is currently used. So more than enough. You can also see that this is Lustre storage. So this is network attached storage. Cool.
One thing,
yeah.
Sorry interruption. This is what is available like in the whole system. For instance, we have seen home that the amount available on work is the thing is on ARCHER2, in order to like to avoid use that a user consumes the whole disk, there are some quotas. So I think to check the home, we have quotas in home and work. To check them, you can either go to save and check the quota user there, but also on ARCHER2 you can check the quota. If I will paste the command in the chat, but there is a way to the quota.
That'd be helpful. Thanks. So this column here also tells us the type of file system. So if you're coming from Windows, you might remember formatting your USB sticks to like FAT or NTFS. This is the Linux equivalent column to that. So you have different types of file systems which are better at different types of things. Not going to cover exactly what those things are, but this basically gives you information about the file systems that are available. All right, the final thing we're going to do before breaking is we're going to look at the available resources on some particular nodes. So if we do sinfo, let's get a summary. So we can see the nodes are basically called by these numbers with this prefix. So it'll be NID 001000 to 6859. So there's a huge number of nodes here. So pick a number in that range. They should all be more or less the same, I think, or exactly the same. And we can ask for some information about resources on that node by typing this command. Here we can see this gives us the host name, so that's the %n, the number of CPUs available, 256, and the amount of memory. So this is in megabytes, I think. So this will be 256 gigabytes. If we go to the next node in the sequence, it should be exactly the same. However, let's have a look at one of these high memory nodes. So that would be 2756, for example. We can see that it has the same number of cores, but the amount of memory is doubled. And if we look at a serial node, and there's 256 cores and more memory by the looks of it. With sinfo, if we bring up the help again, there might be some other format specifications that we can pass. Where it doesn't give us any information there. Go into the manual. Get something a bit more. Oh, here we go. So this is man sinfo, and I've just scrolled down to the -O option, and here you can see it gives us a long list of information in terms of the way we can format the output of sinfo. So we could potentially, for example, try this --long. That might be interesting. A little bit more information. No. Anyway, just so you know, you can change the command to the command had before. This one to give you different types of information depending on what you want to know. All of that is available through man sinfo, or even if you search for sinfo in Google, you should be able to find this page, which is a Slurm command on the internet. Cool. All right. So the key points of that session, just remember that a Hpc system is essentially a very closely networked set of different machines that all serve the task of essentially provisioning compute optimized resources to a large number of users. Hpc systems typically have some login nodes and where you set up your jobs, and worker nodes where the jobs are actually run. The resources available on the independent worker nodes may be different depending on the Hpc system that you're connecting to, and in fact may be different between different nodes in the system that you're actually using. So you should choose nodes that fit the problem that you're trying to solve. Remember that files saved to storage on specific nodes will not be available to other nodes. So in that instance, you have to use some sort of network storage to share information between nodes, or even make it available for download after you've finished your job on the logging node. Okay, Juan's just posted the command for looking at the quota. So if we can use star user because that's a dollar user because that's a variable. Okay, so you can see here my limit is 100 gigabytes. And I assume that because people pay for access to resources on ARCHER2, or they can use funding to get access to resources to ARCHER2, you may be able to negotiate or get into your contract however much resource you need, essentially. For the purposes of this course, I think we've just got quite a small amount of resource allocated for us to do some testing. Cool. So let's go to a break that takes us to 11. If you've got any questions, again, just drop them in the channel, and I'll see you in 15 minutes. We're running a little bit behind schedule, which is okay. I might take this a little bit beyond midday. Hopefully that's okay for everyone. We're going to start now on this section titled Working with the Scheduler. And we're going to first talk a little bit about what a scheduler is, and then move into some examples where we start to submit some simple jobs to the shell. To the scheduler. The person who put together this documentation came up with quite a good example or analogy explaining how a scheduler sort of works. And you can think of like a Hpc system as being a little bit like a large restaurant where there are a number of tables, and the tables sort of define different resources that are available in the system. So they might represent a single core, like each seat might represent a single core, or each table might represent a node with a number of cores associated with it. Or you might have groups that need multiple tables and multiple cores, for example. And the scheduler kind of acts like the maitre d' or the manager to the restaurant. So they have a number of customers coming in, which is you with your tasks. And your tasks might have a number of requirements. So you might need 5 seats or 5 cores, and you might need that on 2 different nodes, so you need 2 different tables. And the scheduler, the maitre d', will look at what is currently scheduled, what's in their bookings book, and see whether there is somewhere where they can place your job right now. And if there isn't, then you're just going to have to wait at the entrance to the restaurant until somewhere where your job fits becomes available. Now, the more complex your request to the scheduler is, like the maitre d' in this instance, more likely the longer you will have to wait. So if you need 10 tables with 5 chairs at each table, you're probably going to have to wait a lot longer than someone who comes in and says, well, I'm a couple, I just need 2 cores on any table. I'm happy to share with someone else. And the maitre d' will probably happily place them almost immediately. The other thing that can happen with the scheduler is people can call up ahead of time and they can say, well, actually, I need these resources to be available on a given day at a given time. And that's called reserving or reservation. similar to just booking a table at a restaurant for 2 weeks from now. And those resources will basically be taken out of the general population and reserved for that particular project to run its jobs when it needs to. So that's sort of kind of how the scheduler works. And the one we're going to be using today, again, is called Slurm. And there are a number of different scheduling softwares available, and the one on your local Hpc system will be determined by what your admin wants to use. But generally, the way they operate and how they reserve and allocate resources to jobs is the same. They tend to manage everything from reservations to working out where tasks can be placed and when they can be run, to the priority of jobs. So some jobs might be given higher priorities, to even things like measuring system usage for charging and so forth. If you're using a different scheduler on your local Hpc system, the exact syntax that I'm going to show you today might be different. The commands might be a little bit different, but the overall concepts should be more or less compatible across all systems. Are there any kind of questions about what a scheduler is, or how it works, or anything that I might have missed there that you have a burning question about? Otherwise, we'll move into starting some exercises where we're going to create some simple jobs for ARCHER2. Okay. So for the next section, I'm going to switch back to the shell, but I'm essentially going to be running through the exercises from this section called running a batch job. Okay, so the first step is we're going to make sure we're in our home directory, which we are, so print working directory. And then we're going to use nano to edit a job script called examplejob.sh. And this is going to be a pretty simple job. We're just going to put the shebang /bin/bash at the top. And then we're going to echo some text. This script is running on with a space here at the end. To get the space, you'll need to have the double quotes. And this -n flag here just tells Echo not to print a new line after we echo this, so that when we print the host name, it will appear on the same line as this text. So remember, host name just gives us the name of the current machine that we're working or running the script on. So we're going to save that out by pressing Control-O, Enter, and then exit with Control-X. You'll then need to make the script executable. So we'll do that with chmod +X. And we can quickly test our script by running it here, example-job.sh. And then we can see that the script prints out the script is running on with our space at the end, and then the name of the host name, which is our login node, LN04. Cool. Now we can submit this job to the scheduler using the sbatch command. So this is another Slurm command which allows us to give the scheduler a job. And we need to give sbatch some information about where we want to run it. So we want to run our job on a standard node. So that's the partition option here, the partition flag. We also need to tell it what type of queue it fits into, which is the short queue, equals short here. And we need to tell it what reservation it belongs to, which is the short reservation. So this short reservation, yeah, one.
The thing is, this is a recent change. The reservation is no longer needed to run on the short queue.
Oh, okay, so we can just drop the reservation.
I just updated the documentation. Sorry about it has been like because yeah, Archer2 previously we had two systems, and there are some changes between these two systems. Yeah, you need just to remember that to run on the short queue, you need to specify the QoS equals short. That's it.
Yeah. Okay. So if I understand right, the short queue is a special queue just reserved for running small jobs. I don't know what the time limit is on the short queue, maybe.
Yeah, that's good. The short queue is normally when you are debugging or you want to try if software works. For instance, in this case, you want to try that the script has been written okay without errors. If you submit to the short queue means that the work time is 20 minutes, but
Okay.
it's long enough in order to do some testing, and the waiting time is much smaller.
Okay. Does using the short queue affect your charging?
Yes, it's there is I need to check. I think there is a queue. I need to check that is something called like a low priority or something like that. That in that queue you need to wait longer, but you are not charged. I need. I'll find the information. I'll put it on in the chat.
Yeah. Do you know if there's a command to get a list of the queues available?
Yes, that is the thing is I don't I don't remember now that, but yeah, that is well, okay, if you give me a second, is here.
Sorry, everyone. I'm learning Archer2 as we go too. It's quite a new system.
I mean that,
so.
yeah, actually, yeah, it's like a good question. Uh, Sorry, I copied it twice. Here is the if you use that, you will see the list of mm, well, it's called quality of service, but yeah, it's a QE. The thing is, yeah, the on Slurm is also in the if you go to the documentation, there is the list of.
Right. Okay. So this tells you. Cool. All right. Sorry, guys. That was a little bit of a sidetrack. Depending on your HPC system, the QoS commands might be slightly different, and you'll need to engage your system help desk to find out what those are or their documentation. But for Archer2, today we're always going to be using this short quality of service or the short queue, essentially, which, as Juan mentioned, is sort of for debugging and testing, and has a wall time limit on jobs of 20 minutes. So this, just gives you the ability to try things out without overloading the login node, but allows you to run the jobs with relatively little, if any, wait time, so you don't have to sit in a queue for a long period. All right, so we're going to submit this job now, which, remember, is going to print out the node name that the job gets submitted to. Oh, sorry, I've misspelled partition here. Oh no, okay, so we kind of expected this output if you're following along in the documentation, but essentially we've been given an error by SBatch, and it says it appears your working directory may not be on the work file system. So because I've written this script in my home directory, that home file system isn't available to the compute node. So this is what I was talking about earlier, where not every file system or every directory that you're working in will be available to the compute nodes. So to fix this, what we're going to need to do is move our script to the work file system. And the work file system is simply located at /work, and it has the same structure as the home directory. So we're just going to replace home with work. So what we want to do is we're going to copy our example job.script to /work / project name / project name again. So remember, you can use tab here to autocomplete, and you can see that all our user directories are in here as well. So you just select your user directory. I'm just going to copy it to mine, and that will do that. And then we're going to move to our user location on the work file system. Okay. And we can double check that we've moved to the right place again by using pwd. Everything looks okay. And we can use ls, see if our job script is here, which it is. I'm just going to remove these out files because they were part of my testing to try and reduce confusion here. All right, so we've moved to the work directory, the work file system, and we've copied our script across again. Let's use the up arrow to scroll back up and find our SBatch command. So we can now press enter and try that again. What happened here? So it's given us a little bit of a warning because we've got no time allocated. So we've got no time flag telling us how long we want to run this job for. And the job has failed because it requires this -- time flag. So let's add that. This job doesn't take very long to run, so let's just say the time is a minute. Okay, so we've added the time flag and submitted a batch job. Everything looks okay. We can look at our job in the queue by using the sq command, and we need to give it our user ID just so that we don't see everyone else's jobs. Currently, my queue is empty because I think this job is already finished. Yeah, so Angie, we said that short, which is assigned to the quality of service flag, is a special queue where you can do testing and debugging. And jobs that are submitted to this queue have a wall time of 20 minutes. So if you wanted to run a long job, this wouldn't be somewhere where you could do that. If you are using a different reservation or a different quality of service type, then you would submit jobs with a different option than short. If you're unsure about what options you should be using for different things on your particular HPC system, again, I recommend you contact support or admin or read any documentation that's available for the system that you're working on. And they'll give you the appropriate arguments to some of these flags. Yeah, good question. So how do you estimate how long it will take to run your jobs? One option is you could take a small set of your data and try and time how long it takes to run a smaller job, say just on the short queue, and then try and scale that up to your full data set. You could allocate a lot more time than you think you need, but that may affect your ability to get the job allocated quickly. So, for example, if you asked the scheduler for an hour, the scheduler is more likely to be able to find a slot where your job fits than if you ask the scheduler for 12 hours or a whole day, for example. But usually the only way to kind of determine what wall time you need is through a mixture of trial and error and small batch testing.
That's a very good question, and also thanks for the explanation was clear. It's just like a, well, not a clarification, but it's like what I see on ARCHER2 that users do, and you can, let's say, avoid it. Most of the users, what they do, because the limit is 24 hours, they say, okay, I will put 24 hours, that's fine. Okay, that's okay, for instance, in the case that you don't know how long the job will run. So to test and to avoid that the job is like the time is shorter, just specify 24 hours. The drawback of this is that to schedule that job could take longer. Once you are more certain on the time, I will advise you to reduce the time, and the job will be scheduled faster. Because I have that, some users normally they just put 24 hours and forget about that. But my recommendation is that to, if possible, reduce the requested wall time, and that will help the scheduler to schedule the.
Yeah, thanks, Juan. Good explanation. Yeah, so that kind of fits the trial and error model where you would just ask for whatever you can get, run the job, check how long it took to execute, and adjust future submissions accordingly. Yeah, we're gonna get to a point where we discuss how to get that information, Samantha. But yeah, good question. Just quickly, I'm going to go back to the shell here. We didn't get any useful output from SBatch. I'm going to submit the job here and then very quickly get the queue back up before the job finishes. So assuming your job is in the queue, you'll get an output like this. You have an ID, so every job has a unique ID. It tells you the partition, so this is the type of node that it was submitted to. It has a name. In this case, it's just given it the name of the script that I submitted, but you can specify a special name if you want. The user, ST here is the status, so this is pending, I think. The amount of time that it's been running for, the number of nodes that you're running on, and then the node list here will be the node that it ends up on. Okay, that's a good one to know. So you can also use sq-me. So this will give you your information. But there wasn't any printout, so I submitted 2 jobs here, but I didn't get any printout. And that's because the job has basically been sent by the scheduler to another node. So I'm not going to get any printout in my local shell. But if we use ls, you can see that we've got 2 files now with this .out extension. And there's 2 files because I submitted the job twice. If I submit it again, we should get a 3rd file, assuming it finishes. Okay, so we can see here that the status changed to R, so that means this is running, and we can see it has a time now, 5 seconds, and it got assigned to the node 1968. It shouldn't take too long to run. So now we have 3 files. The job ID here that we had on that previous job is now associated with one of those output files. And remember yesterday how we were redirecting the std out to a file? Well, Slurm is kind of doing that with your jobs on the nodes. And that output is automatically put into this other file, slurm-1062386, which is our job ID, right? So we output the contents of that, and we can see that the script ran successfully. It printed the text that we expect, and now the host name is the same as the node that that job ran on. And we could look at one of the other scripts here, so 341, for example. I might just use cat instead, so we can see the output above. You can see that was run on the same node. Interesting. I ended up on the same node for both jobs, but maybe not that unusual. Let's see what's in 7.5. Okay, so this one was on a different node. So the scheduler put me at a different table each time I ran this job. Cool. Any questions about submitting that little example job using SBatch just now?
Sorry again for the interruption. There has been previously a question in the chat saying that, for instance, if you have a file in one login node, if you can see the same, I mean, if you need to copy the file to another login node, etc. On ARCHER2, it depends on the supercomputer. On ARCHER2, home is shared between nodes, between let's say, yeah, in nodes. And work, the partition work is shared between login nodes and compute nodes. So the error that you can get if you run a script or you submit a script from the home directory is because the home directory is shared between login nodes, but it is not shared between compute nodes. So you need to copy the files that you need to the work directory and then submit the job. Hope that makes sense. And also, please ask as many questions as you may have, because that's the way of learning, asking questions. Thanks.
Thanks. All right, so the next thing I want to show you is a cool command called watch. But to use this command effectively, I think what we're going to do is just quickly modify our example so that it takes a little bit longer to run. Remember, we can create a for loop. Let's just put some numbers here. What we're going to do is we're going to echo that number, and then we're going to use a command called sleep for 10 seconds, and then we're going to okay. So this just will essentially run the loop 10 times, and it's going to echo the value of S. In this case, should be $1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then it's just going to pause the script for 10 seconds. This is going to allow us to watch the queue a little bit. So again, I'm just going to clear this up. We are going to submit that job. Our wall time here is going to be a little bit longer because I've got 10 times 10 seconds of sleeping, so I need to make my wall time a little bit longer. In this case, I'm going to go up to 5 minutes. Then the watch command essentially will allow you to rerun a second command, in this case sq-me, repeatedly in every n seconds, and in this case we're going to run it every 10 seconds. So sorry, this is double me. And essentially this clears the screen, and we should see this time here update every 10 seconds, so we can see how long our job's been running for. And this allows us just to quickly monitor the status of our job or jobs as things change. If we want to get out of the watch command, we can just hit Control-C. You can use watch with any other types of commands that you want to watch, that you want to repeatedly run. It's quite a useful one to know about. Another interesting way to use it would potentially be to run it with ls. In this instance, we could wait for extra files to arrive as jobs are finished running. Any questions about watch or that example? Yes, there is. We're going to get to that a little bit later, I think. Sorry, the question was, is there a way of seeing all the past jobs? I believe that's with the saccount command. Right, so in the documentation, the command given to SQ is -u and then your user ID. So this is essentially a filter to SQ. If you were just to run SQ by itself, you'll get a huge printout which shows every job currently in every queue that the scheduler is trying to deal with. And this can be useful maybe if you want to look at what's going on the cluster, but most of the time we're only ever really interested in what we're doing on the cluster. And the way you can filter that SQ list easily is just to use the -u and your username command. And there is some shortcut, or some shorthand for that, which is the --me. So this essentially tells SQ that you only want to see jobs related to yourself. You want to see the loop again. Hold on. Let me bring that up. I can paste this in the chat if that helps. All right. Cool. Let's. Okay, so Juan's just posted the way to see the jobs on the account. I guess S is the start date at which you want to see jobs back to. Is that right, Juan?
Yes, so I didn't specify that. Yes, it's, you need to specify the start date, user, minus X is to see like a better list of. You can try without the minus X, and you will understand why. If you don't use minus X, you will have like 3 entries rather than one.
Okay, so let's just try that out. I'm only going to go back to yesterday so we can see what jobs I've run now. And there you can see the 4 jobs that I've run so far today. Cool. All right. I'm going to keep moving because we've got quite a bit of content to cover here related to the scheduler. You can look at a lot of the options that are available to SBatch, again by using the --help flag, or by going to the manual via Google, or using the man command in the shell itself. And it can be a little bit overwhelming at first, but there are a large number of flags that are kind of grouped into different things that you might need to do. Most of these are not that useful, but the ones that allow you to customize, sort of here at the top, your call to SBatch can be quite useful. A good one to know, for example, is the job name flag, or the --J flag. We can give our job, go back to here, we can give our job a name. So if we do it job name, that dash job name. So let's call it my job, something equivalent. Example job.sh, there we go. So in this case, time, I need a space here. It's a little bit funny here with my terminal. Right, so our job got submitted, and if we check SQ again, my jobs, we can see that the name has changed now to match the name that I gave the job. So this is a nice way of differentiating between particular jobs that you might have run. You can also, rather than typing these flags into the command line all the time, actually specify them in the script that you want to run. And the way that's done is by specifying a comment, and the comments in bash scripts start with a hash, and then putting a special flag for sbatch called capitals or sbatch, and then you can put the flag and the argument that you want to pass. So in this instance, I could put job name, and the value I could be on script, something like this. So now I save that out, Control O, and then exit, Control X, and remove that job name argument and resubmit. Then we go back and look at the queue. You can see that we now have another job running here called from script. Okay, which was it's kind of truncated here, but you get the idea. And you can actually specify all of these options in your script. So you can spread these across multiple lines. So we could have another one here, sbatch partition standard and sbatch QoS short. Those are all the ones I was running. Oh, the wall time. This one. So that's going to be 5 minutes. Okay, so you can kind of specify all of these arguments within the script, which saves you typing them onto the command line every time. And then your call to sbatch would simply become sbatch in the script. And you can see that that job has been submitted here. Okay. Cool. This Control C is not working. That's a weird one. I might have to leave you with one on that problem, Johnny. So is there any questions there about setting the name of the script or adding the options to your script directly? Did anyone have any problems with that? Okay, cool. So in the next section, we're going to talk about how you request resources. So some of the other options that you might want to pass sbatch or some of the other queue submission programs relate to the number of resources that you want to request for your job. So in this instance, I'm just being allocated a single node, but we may want to specify that we want more than one node, or that we need to run multiple tasks per node, or that we want multiple CPUs per task, for example. So we can become a bit more granular about how we're going to request resources, and then that will affect our ability to submit our jobs through the queue, and how the scheduler will distribute our problem across the system. Some of the key resources that we will need to know about. Let's just bring up the help here. So we might want to know, for example, how many CPUs per task we have. So this is the number of cores that we need to assign to each parallel process. A process is essentially what happens when you start a program. So if you start Python or you start R, that is a process, and then you can assign to that a number of cores that it might have available. You might want to ask for, where's the N here, a particular number of nodes. So we could ask for more than one, for example, or up to as many as you need, given the size of the Hpc system that you're working on. Obviously, the more nodes you ask for, the harder it will be for the scheduler to find space for you to work. You might want to specify a number of tasks per node. So this is where you might have a number of models that you want to run that are not related to each other, so they can run in parallel on the same node. And then the last one, which we've already looked at, that you need to know about is time. So this is the wall time limit. So sometimes you'll hear people talk about wall time, which is the time it takes when you look at a clock on the wall. And other times people might talk about compute time, particularly when they're talking about charging models. And this is the amount of time that you have requested of resources. So that might be based on the number of cores that you're using. So if you used 2 cores for 1 hour of wall time, then you would have used 2 hours of compute time, for example. So there is a little bit of a difference to be aware of there. Cool. Let's move on to the next example. Where we're going to see what happens when a job we have overruns the time allocation that we've asked for. And we can do that by going back to our example here. And let's ask for a very short amount of time now, just 30 seconds, say. If you haven't put this loop in, you can just put in a simple command like sleep for 60 seconds. So we know this script is going to take at least 60 seconds to complete, but we've only asked for 30 seconds of actual compute time. So what will the scheduler do if our script takes longer to run than the amount of time we've asked for? I'm going to put in a little bit of a check here to make sure that we know the script finished. So if the script makes it to the end, then it will print these values. I'm just going to actually get rid of this loop for a moment. Okay. So let's submit the script. The job's been submitted. Let's watch the queue, see when it finishes. We only asked for 30 seconds of wall time, so essentially the scheduler will terminate our job when we get to 30 seconds. 24, 29, and 34. Okay. Will this cancel? Okay, I'm a bit surprised this is still running. let's see what the output of that job was. So remember, we can look at the jobs we ran. You can see that so here, right, we can see that the state was timeout. Okay, so it took a while, but the job did get cancelled. I wonder what the output of that job was. So that was 102.6474 for me. And the script's still finished, so maybe it takes a little bit longer for the scheduler to cancel a job than the 30 seconds we gave it. Not sure if you have any comment on that one in this instance.
Yeah, because okay, time. No, because I think okay, it's 30 seconds. I'll double check that because not sure if maybe it's taking is 30 minutes or no,
You
should
think
be no, it's 30 seconds because otherwise the short queue will complain.
Yeah, I mean, I can be a bit more specific. So this would now be hours, minutes, seconds. Let me try and extend this a little bit, and we'll come back to this and see if this job fails. Okay, so you're going to resubmit that job. All right, while we're waiting for that to finish, did anyone have any questions at the moment about the things we're looking at related to the queue? There's an interesting note here in the documentation that talks about the cost associated with jobs. So on ARCHER2, if you request 12 hours of compute time, for example, but your job only takes 4 hours, you will only be charged for the 4 hours that you used. So even though you request a little bit more, you won't be charged for your request more, you'll be charged for your actual usage. That may be different for different. Yeah, so you're not penalized from a cost perspective, Johnny. The question was, are you penalized for misestimating runtime? Not from a cost perspective, but the penalty is that the scheduler will take longer to find the appropriate resources for you to run your job. Now, the jobs we're running now are trivial, so they run almost instantaneously. But when your jobs become significantly larger or of appropriate size for a Hpc system, then it could become more difficult to instantaneously allocate resources. Oh no, I don't think the scheduler has any kind of memory or knowledge of your history in terms of what you're submitting to it. It's not quite that intelligent. All right, let's just have a quick look here at our job finished. Okay, it says timeout again. I'm going to see if the output has come through. This was 6491. Okay, so now it just took the scheduler a little bit of time to actually cancel the job on the node. We didn't give it enough time to do that. So if your job is cancelled early, you'll see an error like this. So essentially it's just telling us we hit the time limit of our job. And in that instance, you'll either need to increase the time limit to complete your job or improve the way that your job is working on the node so that it runs within the time that you've allocated. to check jobs just in your queue or in all queues? So if you want to see every job, then you just have to put the SQ command. Remember, this gives you a full list of everything that's currently submitted. Anything you see here with an R is currently running. And if you see like a PD, maybe we can see, here we go. So these are all pending, these PD ones. So they're waiting for allocation to become available. Cool. Let's say you have, I'm going to edit my job again here. So that, that's not what I wanted to do. Edit it. I'm going to edit my job so that it runs for, say, 5 minutes, or even 10 minutes, say. Because, and I'm going to increase the sleep time here, 560 or something. So it gives me a chance to show you how to cancel a job. So let's say we start a job, we realize we've made a mistake, or maybe we've submitted multiple jobs and we've got some early results back and we're not happy and we need to cancel the job and make some edits before we resubmit. You can do that using the scancel option command. So I'm going to submit this job, and this job again has a unique ID, and we can look at the jobs that we've got running with sq-me. That ID was 6512, so we know this job's going to run for a while, but I've decided that I don't want to actually run that job to completion. In that instance, I can use the scancel command, so this scancel, and I need to pass it the job ID that I want to pass, that I want to cancel. So in this case, this is 102.6512. And I could actually pass it multiple job IDs if I have multiple job IDs that I want to cancel. So I could also pass it that one. Scancel. My spelling's atrocious. So that will then send a message to the scheduler and tell the scheduler that actually we changed our mind and we want to cancel the job. If I now go back to SQ, you can see that my two jobs have been removed. And if we have a look at our job history, we can see that the job that I submitted last there, the 65121, we actually cancelled that. So it tells us that we were responsible for ending that job early. You still get an output from that job that you cancelled. So anything that you ran before you cancelled it should still be written to file. But you'll also get an error at the end telling you that it was cancelled and when. Okay, so how would you see preliminary results? If your results are being saved to the shared disk, you can look at them on the login node. Don't have an example script that I could do just now. All right, this is a good challenge. Let's go back to our job
I
here.
think the is like to see, for instance, when you execute the for loop, you can read the output file, and you can see the stage of the.
So yeah, anything that's being output to the standard out, the SDT out by your program will be available in that .out file. So that .out file is written to every time something happens on the worker that prints to the shell. If you're running more complex programs, some of those programs might save out intermediate results. So those intermediate results can obviously be looked at and interpreted as long as you don't change them or they're not required for future processes by what's running on the worker. If you're doing stuff on the worker, I don't know if on some systems they'll let you SSH onto a worker, but I don't know if they'll let you do that here. No. So on ARCHER2 they don't let you SSH onto the individual worker nodes themselves, but on some systems they might let you do that, and that's a way you can also get onto a system to monitor what's happening to a job on the node. But for Archer, you'll have to push results back to the work directory to be able to see them while the job's running. And you can kind of set up your script so that if you're saving things out onto the scratch drive of your node, that those things are periodically copied back to the worker. Cool. Right, so we've probably got about 10 to 15 minutes left in this section. Are people happy to continue going and just shorten lunch a little bit, or do you want me to come back to this after the lunch break? We can go for a poll here. Okay, cool. All right, cool. Let's keep going then. So there are, with Slurm and most of the other schedulers, different types of jobs that you can run. So SBatch isn't the only job that you necessarily might want to run. A common one that allows you to run a program with Slurm is called just srun. And again, you need to specify the partition and the quality of service and the time. And srun doesn't execute a batch script. It just basically executes a command. So in this instance, we could just execute the command hostname, for example. This then basically will run the job and return some output directly to the shell that you're working in. We could also submit different commands, so we could submit like echo, this is from a node, like that. That'll go away and run. It'll tell you what it's doing, and then it will come back. Oh, sorry, I misspelt echo maybe. Oh, because it needs to be, it doesn't like these arguments. You have to specify them separately, I think. I'll just skip over that. But you can also ask for what are called interactive sessions. So sometimes you might want to get onto a node to do some debugging, or you might want to just run some simple tasks that you can do in the shell itself. So to get an interactive session, again, you need to specify the partition and the quality of service. but you can also specify this option -pty, which essentially drops you into a shell session on the node, and then we can ask it to start bash. Oh, I need a time as well, sorry. So let's say we want a shell for 5 minutes. This will run the job, wait for the resources, and now it's dropped us onto a node. So you can see we're on the node because the host name here in my prompt has changed. And I can type host name here. See that I'm on that particular node. If I go to /home, you'll see that there is absolutely nothing in here. So this doesn't have access to the home directories like when we were on the logging node. You can go back to work here, and we can see that all those files are there, including all the outputs from the other jobs that we've run. If we want to exit this session early, it's the same as logging out of Archer. We just type the exit command, and we drop back to the login node where we started the job from. Yeah, so the question is, what's the utility of the session within the session? Let's say you need to do some quick post-processing, or you want to run a couple of scripts that don't very long, but they're just a little bit too big to do on the login node. Then you might just ask for a quick interactive session, or even a longer interactive session, so you can do things. It also allows you to have the resources allocated. You can do some editing of the code or write some quick scripts on the node itself and run and test them while you're there. So it allows you to do some more interactive style debugging if that's what you need. You can use it to run tests. So you might want to do like some optimization tests, or check like some run times where you have access to actual resources and so forth. Yeah, so you don't have to write things in bash. While you're doing that debugging, you can edit Python scripts or R scripts, or you can even edit C code and compile it within that session. It's essentially an interactive shell, but it gives you an isolated set of resources that you can use to your heart's content, rather than necessarily impacting people on the logging node. What would you see? Yeah, so let's say you have written a function. I'm not sure what language you're using, Liliana, but let's say you've written something in Python or R or whatever your preferred language is, and you think you've got it all working, and then you submit it to a node, and every time it keeps, conking out. You have errors, and you're just struggling to understand why it works on your computer but doesn't work on the node. Well, you could start an interactive session, run the code on the node, and you would get the stack trace and the error back that you would normally get if you ran your code locally. And then you can start to edit it potentially and debug it on the actual system that will be running it. Now, in those cases, you may not want to use all the data or run a complex problem that you're trying to solve. You might want to create like a smaller problem or data set that allows you to replicate the problem, but runs fast enough that you can iteratively address the problems with your script so that it runs on the system. Okay, so the last section here that we're going to tackle before lunch is about running parallel jobs. So this is a different type of job where you might want to use more than one node to compute, or more than one core even to compute a problem. We're going to edit a file now, or create a new script called run sharpen. And sharpen is a program that basically takes an input image and defuzzes it. Essentially, it sharpens the image by passing a filter over it. That could be quite a compute-intensive task, but we've got like a little baby example that we're going to use for today. And I put the .slurm extension on the end here because I know this is a job that I can submit to, sorry, a script that I can submit to srun or sbatch. I prepared this a little bit earlier, but it's more or less what we've had before. We've got a few arguments that we're passing to the srun command. So we're going to pass this to srun. And so this is essentially, we're going to run this script. It's going to pass all of these arguments to srun. And sorry, it's going to pass these to sbatch. So we're going to submit this script to sbatch, and then it's going to use srun essentially to run our MPI code. The key ones here in terms of running the parallel job are that we're going to run this on just one node for the moment, but we're going to ask for 16 cores or 16 processors on that node. This is not actually the sorry, it might actually be so this isn't exactly what I need it to be, because these lines have changed. So all of this should be okay, but the way the script was run changed a little bit since the last session. We need this to add to our path. And we'll talk a little bit about the path this afternoon, but know for the moment that we're basically adding the location of the binary that runs this code. And we're creating a variable that points to, so we're creating a variable called fuzzy input here that points to the, sorry, to the input file that we're going to sharpen. This is just an image file in PGM format. And the thing we need to do is copy that input to our current working directory as well. And the binary is just called sharpen-mpi. So in summary, we're going to submit the script to SBatch. We're going to ask for 1 node and 16 cores. We're going to add some variables to the path and a variable called fuzzy input, which is basically the location of our input data. We're going to copy that input data to our current location, and then we're going to use srun essentially to run this process. To submit the command, we're going to use sbatch and then the run sharpen.slim. See our job's been submitted. Have a look. You can see we're on 1 node. That's fine. Hopefully it doesn't take too long. And job's done. And we can check the output of that job, which was slim 1026.573 for me. And we get this output where Sharpen has found the image, given us the image size, read the file, and we can see that it's running on all these different cores of the same of a single node. So this is just some nice output that Sharpen gives us so we can see what is going on. You'll also see that we have now a file called fuzzy.pgm in our current working directory, because our script copied that fuzzy.pgm input from the shared folder. And we also have an output sharpen.pgm, which was the output of our job run. Yeah, so Susanna's just asked what partition is. Partition refers to the type of node that we're running on, or that we're requesting. And remember, we had a look right at the top with sinfo -s, and we can see that we've got 3 different types of partition available within the ARCHER2 Hpc cluster. Just the standard one where there's over 6,000 nodes of that type. We've got the high memory versions, so there's a bit over 1,000 of them, and we've got the serial version. And these are just different types of nodes, so they have specific applications. In some clusters, you might get different architectures. So you might not have an Intel node, you might have an AMD node, an ARM node. You might have, you might also have specialized GPU-specific nodes. You might have nodes with access to a large amount of scratch space so that you can run things locally. The partition was standard for all the jobs today. That's the only partition we're using. Let me post the code here so people can see. This is all available on the scheduler page documentation that we've been working through today. All right, so that I'm going to wrap things up there for lunch. Obviously, aware you guys got other things you need to do. Let's get back together at 1:30. That's a little bit over an hour from now, and we'll continue with this afternoon session. If you have any more questions from this morning's topics or even things related to yesterday, just drop them in the chat and we'll try and address those over lunchtime or at the start of the next session.